Hey guys, welcome back to another video. Today what we're going to do is we're going to talk a little bit about orbitals. What are orbitals? How do we how do we characterize them? What kinds of orbitals are there out there? We're also going to talk a little about quantum numbers, which is going to be super fun. But let's go ahead and get into this. Let me pull up the old paint. Okay, finally, at long last. I can get my screen to share. Okay, yeah. So let's talk a little about orbitals and what they are and what they mean and all these sorts of things. So let's go back a little bit to our picture of the atom. So recall we have an atom with a nucleus here in the middle. Let's give it, I don't know, 4 protons, right? And the way we've been describing it so far has been we'll have like a little ring, a little orbit that the electrons will follow, right? And they just kind of like move around in this circle around the nucleus. There's one downside to this. So this is the idea that Bohr had. There's one downside to this, and this is that we have something called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle. That's not like the most important principle to remember, but it is the basis for what I'm about to say next. So according to the Heisenberg uncertainty principle, you cannot simultaneously know for an electron, you cannot simultaneously know its location and its direction. In fact, the more you know about the location of the electron, the less you know about its momentum in any other given direction. So that's a really big issue. The more we know about it in one context, the less we know about it in another context. And so that means that if I simplify it a little bit, that means that we can never actually take an electron, like a given electron right here, and then track its movement, right, around the nucleus, right? Instead, what we have to do is we have to work with probability. So what do I mean by that? Basically, what I want you to envision is let's draw a little cube here. Let's give it something like this. Let's call this A to D, and let's call this 1 through 4. Basically, what we have to do for electrons is we have to be like, dear Mr. Electron, are you at A1? And the electron's like, no. And then you're like, are you at A4? And the electron's like, no. And then like, are you at C1? And it's like, no. And then you ask, are you at 2B? And he's like, yeah. And you're like, okay, what about 3B? And he's like, yeah. And what we can start to do is instead of tracking the movement of a given electron, all we're going to do is we're going to try and figure out what's the likelihood that if I look in this location, I'm going to find an electron there. What's the probability of finding an electron? Now, what you can start to see is that there's a little shape associated with where the electrons are located or where you're likely to find an electron. Okay. There's as we would describe it, this would be a region of electron density, a place where you're likely to find an electron. Now, these regions of electron density, right, we call these orbitals, right? So an orbital, a region of electron density. Okay. And these regions of electron density, again, this is just a location that you're likely to find an electron. These regions of electron density, they can take different shapes depending on how far away the electrons are from the nucleus, depending on a whole host of other factors, some of which we're going to cover today. But first, I want to emphasize what an orbital is. So it's a region of electron density, a spot where you're likely to find an electron. Okay, so that's the first big concept here. What exactly is an electron? I want to spend a little bit of time now talking about so-called quantum numbers. Now, what quantum numbers are is these are ways in which we're able to specify where an electron is or the characteristics of a given orbital, right? By that, I mean the characteristics of a region of electron density. quantum numbers. Now, there's 4 different quantum numbers. We're going to cover 3 of them today and then 1 later on. The first, the primary quantum number, is n. Then we have one which is L. Then we have one which is M sub L with a subscript L. Okay, so we're going to go through each one of these. The n value, maybe you guys will recall this from our previous conversation on electrons. This is what we would call the integral quantum number. The integral quantum number. But all of this really means, you can kind of think about this as being the distance from the nucleus. Distance from nucleus. Okay. So if I have if I go back to this nucleus right here, the electrons that are at this radius from the nucleus, we would say that these have like an n of equal to 1. And the electrons with this radius, we would say that has an n equal to 2, right? So the n, the n quantum number, the integral quantum number, tells you how far away the electron is from the nucleus. And as our n value increases, right, the further away the electron is from the nucleus. Okay, that's the first one. So I could ask this question. I would say, hey, let's say I have an electron with an n of 2 and an electron with an n value of 4, right? Which one of these is farther away from the nucleus? And you would say, well, the electron that has an n value of 4, because as the n value increases, the further away the electron is from the nucleus. Okay, so that's our first one. Now, as the electrons get further away from the nucleus, right? So let's take a look at these ones. Let's say I have an electron here. As the electrons are moving further away from the nucleus, because they're further away, they actually have a little bit more room in which they can organize themselves, right? They have a little bit more room in which they can make all these different kinds of shapes, right? And so what that means then is that as your n value increases, right, you start to unlock different shaped orbitals, right? I drew a little sphere right here, right? But as the n value increases, you're going to have different shaped orbitals. So instead of a sphere, you have something else like a dumbbell or a clover or what have you. We're going to unpack that in a second. But that's what the L value is referencing. So the L value stands for angular momentum. Angular momentum. But for the purposes of our discussion, we could just say this is a shape. Okay, what's the shape of the orbital? Right? N value is how far away is the orbital from the nucleus. The L value says what is the shape of the orbital. And we have a code that we utilize to figure out, to associate numbers with shapes. Okay, so let me land the plane real quick. So if I have an L value, I make a little table for here, you would do well to write this down as well. Okay, so if my L value is 0, right, then I have a sphere shape. We'll talk about that in a second. And the orbital is an s orbital. Okay, if my L value is 0, I have what's called an s orbital. If my L value is 1, right, then I have what's known as a p orbital. That's the weirdest P I've ever drawn in my entire life. Okay. If I have an L value of 2, then that's a d orbital. And an L value of 3, that's what's known as an f orbital. These are the 4 different shapes or categories of orbitals that we're going to be covering. There are, to my understanding, 3 additional other shaped orbitals, G, H, and I, but that is not what we're going to be talking about in Gen Chem. So that means that, so again, just to recap, if I have an L value of 0, that means I have an s orbital. If I have an L value of 1, that gives me a p orbital. 2, D, 3, and F, right? We're going to unpack what that looks like later on. But first off, I'm just drawing the parallel between, or the link between the L value and the name of the orbital. Now, I mentioned a second ago how as the n value increases, you start to unlock more of these different orbitals. And the way you know which ones you have unlocked is you have a simple equation to solve for acceptable values of n, right? So at a given n value, my acceptable L values range anywhere from 0 to n minus 1. Okay? They range anywhere from 0 to n minus 1. So, for example, let's say that I have an n value of 1. It ranges anywhere from 0 to 1 minus 1 or 0. Okay? So that means I have access to an L value of 0, right? If I have an n value of 2, right? So if the electrons are now a little bit further in if the n value is 1, right? Then I have access to 0 all the way to 2 minus 1, which equals 1. So that means I have access to the 0 L value and the 1 L value. I'm going to erase this M sub L because that's going to be encroaching on our stuff. Okay, so know what this means then. This means that at every single n value, you're going to have access to an L value of 0. So that means that at every single n value, you're going to have access to the s orbital, right? At an n of 2, you have access to the s orbital and you have access to the p orbital. At an n equals 3, right, you have access to the s because you have the 0, p because you have the 1, and d because you have the 2, right? So as the n value increases, you start to unlock different L values. And as you unlock different L values, that means you have access to different orbitals. Okay, so that's what the L is representing. Depending on the type of L value you have, that tells you what the shape we're working with. Okay, so that's the L value. So that means, let me just do a real quick practice problem over here. So let's say that I have an n value of n equals 3. And then I said, hey, is this an acceptable n value? You would be like, well, the L values range anywhere from 0 all the way to n minus 1, so 3 minus 1. So that means 2. So I have access to 0, 1, and 2, right? This L value is 2. So yes, this is an acceptable L value. Let's say that I had an n equals 2, and then I'm like, can I have an L value that equals 2? Right? Then okay, if I have an n value that equals 2, then that means that I have access to 0 all the way to 2 minus 1, which equals 1. So I have access to 1 and 0, right? L does not fall within that set, so that means this is an unacceptable L value, okay? That's kind of how I'm going to phrase these questions. I'll be like, hey, given this n value, is this L value allowed? If it's not, then say, no, Dr. K, you big silly. Okay, so that's what our L value represents. It represents the shape of the orbital. We'll talk about the shapes here in a second. And there are certain shapes that are allowed given the n value, okay? Now, after this, we have what's called the M sub L value. The M sub L value, let me be precise in my language here. This is what's called the magnetic quantum number. The magnetic quantum number. Okay. Now, the magnetic quantum number, think about this as more the orientation of the shape. So if L was the shape, then this is the orientation of the shape. Let me give you an example of what I mean. Okay. So our p orbitals, I'm going to scroll up a little bit or scroll down a little bit. Our p orbitals look a little something like this. They're like a little dumbbell. Okay. But that dumbbell, it can be either oriented in this direction, like a horizontal sort of way, or it can be in like a vertical sort of way, or it can be like a coming out of the Z plane out towards us type of way, right? There's multiple different ways that this particular shape can be oriented. I'm going to say that again. There's multiple different ways that this particular shape can be oriented. And each of those different configurations you need to take into account. And that's what this M sub L value is talking about. Okay. So for example, this p orbital, which looks like a dumbbell, it can either be this direction, or it can be this direction, or it can be this direction, right? And the M sub L tells you what configuration that particular shape is. Okay. So as you might expect, there's different possible configurations given the type of orbital that you're working with. I'm going to say that again. There's different possible configurations depending on the type of orbital. Now, the way we know how many configurations there are, right, is based off of the L value. So just as the N value, right, gives you a certain amount of acceptable L values, there's a certain amount of acceptable M sub L values given the L value, okay? So our possible M sub L values range anywhere from minus L all the way to plus L, okay? So for example, let's say that I have an L value equal to 0. That means I can go all the way from minus 0 to plus 0, which is to say we have exactly one possible configuration. So importantly, I'm going to emphasize this again. At an L of 0, you have only one configuration. Okay. Now let's say that I have an L value that is equal to 1. That means I can go all the way from minus 1 to plus 1. So that means I have access to a configuration that is minus 1, a configuration that is 0, and a configuration that is plus 1. I have 3 different configurations if I have an L value of 2. Okay. I'm sorry, if I have an L value of 1, right? Because I have to plug this into our equation here. 1, if we go from minus 1 to plus 1, that means I have 3 different configurations. Okay. If let's finish this. Let's say I have an L value of 2, right? That means I can go all the way from minus 2 to plus 2. So that means I have minus 2, minus 1, 0, plus 1, and plus 2. So I have 1, 2, 3, 4, 5 different configurations if I have an L value of 2. And finally, if I have an L value of 3, I can do the exact same thing, but I end up with 7 different configurations. Okay, so let me reemphasize where we are so far. First off, we have an N value. That's our integral quantum number. That just tells you how far away is this particular orbital from the nucleus. How far away are we from the nucleus when we're talking about this particular orbital? As the N value increases, because you have more space, these orbitals can configure themselves in different shapes, right? That's what the L value is representing. The L value tells you, based off of the number, what's the shape of the orbital, right? We have a little table here that says what shape or what orbital type corresponds with which L value. So at an L of equals 0, you have an S orbital. L of 1 equals a p orbital, 2 equals a d, 3 equals an f. And importantly, as the N value increases, you unlock different shapes. That means you unlock different L values. And we have this simple equation which says the acceptable L values given an N value are 0 all the way to N minus 1. So you're always going to have the S orbital, and then whether or not you have the p or d or f depends on your N value. Okay, so L is our shape. Our M sub L, so you're locked into your shape, right? But then you have a different configurations of that particular shape, right? And the amount of different configurations that you have access to is determined again by your L value, taking you all the way from minus L all the way to plus L. So if I have an L equal to 1, then I have only one configuration. If I have an L of 0, I have access to one configuration. If I have an L of 1, I have access to 3 configurations. An L of 2, I have access to 5 configurations. An L of 3, access to 7 configurations. Okay, so these are all different ways that we can talk about the type of orbital, how far away it is from the nucleus, what is its configuration. Okay, so those are the big quantum numbers. There are a set of acceptable quantum numbers and sets of unacceptable quantum numbers. So let me go through an example of what a question would look like. And there's one more quantum number, but it's really, really easy. So we're just going to ignore it for now, and I'll explain it later on. So let's say that I had this series of quantum numbers. And then let's say my M sub L is equal to 0. Let's do this one. N equals 3. L equals 1. M sub L equals minus 1. Let's do another one. N equals 2. L equals 2. M sub L equals minus 1. Okay, and I would ask you, all right, which of these are acceptable quantum numbers, which of these are wrong, how would you change it? Okay, and we got to go back to our little formulas to figure out whether or not they're acceptable or not. So I always start off with n. All right, I have an n value of 1. Fine, that's great. Given this particular n value, I have access to L values that range from 0 to n minus 1. So 1 minus 1 is 0. So I should have only access to one L value, which is 0. So this is fine. Given our n equals 1, I should have an L value of 0, and that's it. So that one's good. And then our m sub L values, remember, those range anywhere from minus L to plus L. So in this case, minus 0 to plus 0. So that's 0 as well. So this works just fine. That's a good set of quantum numbers. This one right here, we have an n value of 3. So that means I have access to L values of 0, 1, and 2, right? L falls within that series. So these are both good, right? Given my L value, I have access to m sub L values of minus 1, 0, and plus 1. This falls within that series, so we're good on that one as well. So this is a good set. This one right here, I have n equals 2. That's fine. That means that I only have access to L values that are 0 and 1, given our previous equation. L doesn't fall within that set, so this is wrong. If I changed it to L equals 1, that would be just fine, because remember, we have access to 0 and 1 given our n value, right? And then if I had an m sub L value of minus 1, that would be allowable given the L value as well. So if I just change this to L equals plus 1, then I'm fine. Okay, so that's the kind of question that you can expect from me. I'll be like, all right, hey, here's a series of quantum numbers. Are these acceptable quantum numbers? Okay. Let's move forward a little bit here. Okay. Indeed, let's talk a little bit about, I'm going to stop sharing this screen and share a different screen with you guys. Okay. All right, let's go to, so I mentioned a minute ago about different kinds of orbitals. Close this out. You open this up like zoinks. Okay. Let me give some room real quick. Make sure that my screen still looks good. All right, cool. All right, so this would be instances where we're talking about the different shapes of the orbitals. So remember that there are four different shapes that we talked about corresponding to 4 different L values. So if we had an L equals 0, then that's an s orbital. We have L equals 1, that's a p orbital. L equals 2, that's a d orbital. L equals 3, that's an f orbital. Okay. So this first one is the s orbital. So this is when L equals 0. Okay. When L equals 0, you have this little spherical looking thing. So this is an s orbital. S orbital. It's just a little sphere, right? Now, as the n value increases, right? As the n value increases, you remember you have the access to the sphere orbital at every single level. So as the n value increases, all that's happening is it's the same shaped sphere. It's just it's getting bigger and bigger because it's that the electrons are at a further distance from the nucleus. Okay, so this is our s orbital. It's pretty straightforward to memorize. It's just a sphere, right? Next up, we have one more thing. Also note that because it's a sphere, there's really only one way that you can configure this. No matter how you look at it, if you grab the sphere and rotate it around, it's still essentially in the same configuration, regardless of how you look at it, right? Which is why we only have one configuration for the sphere, right? So if L is equal to 0, then that means we only have access to one configuration. right? That's what our m sub l value tells us. Well, that checks out. That's nice. So that's our s orbital. Next up, we have our p orbitals. Oops. Sorry, I'm trying to clear out some of this background stuff. Next up, we have our p orbitals. P orbitals. This is when we have an L value of 1, and our m sub L values range from -1 to +1. Okay, these look like a little dumbbell. Someone told me, one of my high schoolers told me that this one kind of looks like a Pringle, which I guess is a way to remember that it's a p orbital, but either way, doesn't really matter. I just remember p as being dumbbell, right? So this is a p orbital. It's a dumbbell looking thing. Because of its particular shape, right, there's multiple different orientations or configurations that it can take. And specifically, there's 3 different configurations, right? We would call this the px, the py, and the pz. You don't need to memorize these different configurations. All you need to know is that there are 3 different configurations given this L value. And you can either memorize that or you can solve that by utilizing that equation of minus L to plus L. Okay, but these are the p orbitals. Next up, we have the d orbitals. All the d orbitals are is the baseline organization or orientation is this kind of clover shape. So this is it's a clover, right? And this is when the L value is equal to 2. Okay. If the L value is equal to 2, right, then that means that our m sub L values range anywhere from -2 to 2. So be -2, -1, 0, 1, and +2. Okay. So 5 different configurations represented by these guys right here. This starts to get a little funky because we start to see things like XY, YZ, ZX, all these different things. Again, you don't need to stress about the actual naming of the configurations, right? But this is what the d orbital looks like. It looks like a little flower clover. That doesn't seem too bad. It's kind of heartening on a cold day such as this. Right, so that's our d orbital. Again, this d orbital, you only unlock this if our n value is 3 or higher. Okay, there's no such thing as a d orbital that exists at an n value of 2 or an n value of 1. Okay. The final one that I want you guys to cover is what's called the f orbital. F orbital is so weird. If the d is a clover, if the p is a dumbbell, if the s is a sphere, this one is just because as the electrons are getting further and further away, they can take all these odd configurations. This one, I like to start with this one. It's like a weird, like, I don't know. It's like a bunch of little stones that circle around and are like making a little cult thing. I don't know. Maybe they're about to, I don't even know what they're doing, but regardless. So this is what the f orbital looks like, right? Now remember, the f orbital, we'll just call this, I don't know, random shape. You know what? We'll call it Stonehenge. That feels more appropriate. Is it Stonehenge or Stonehenge? We're going to go with that. Stonehenge. All right. So Stonehenge orbital looks like that. This is when our L value is equal to 3, right? So that means that we have access to m sub L values ranging from -3 all the way to +3. So -3, -2, -1, 0, +1, +2, oops, +3. Okay. 7 different configurations given the f orbital. Note that because the L value is 3, that means this doesn't unlock until n equals 4. You're never going to have something like an f orbital at an n value of 3. Okay. So those are the 4 primary orbitals I want you to be able to use. I want you to be able to identify whether or not quantum numbers are appropriate, right, given like a list of quantum numbers. I also want you to be able to identify the shape of the orbital or the name of the orbital based off of sight. I want you to be able to say, hey, look at this orbital. How many L value, or what is its L value? I want you to be able to be like, okay, here's the shape of the orbital. How many different possible configurations does it have? Okay, so you can either just straight up memorize them, which some folks like to do, or you can just remember the formula, and some folks find that more easy as well. Either way, I can start to piece together a little table for you if that would be useful. Um, just let me know. But I did mention there are some other wild orbitals. This is what's called a G orbital. This is when we move up past F orbitals. There's a bunch of wild shapes that you start to see. But again, that's not really what we're focused on today. So, okay, let me see if I can recap where we're at. Remember, we had we talked a little about the nucleus. We talked about, and the way that electrons are organized around them. We talked about what an orbital was. It's a region of electron density where you're likely to find an electron. We talked about 4 different quantum numbers. The N quantum number, which is the distance from the nucleus. We talked about the L quantum number, which specifies the shape of the orbital. We talked about the M sub L value, which is the configuration of that specified shape, right? And then we talked about what values were allowed as you move from N to L and as you move from L to M sub L. We covered the shapes of the different orbitals, how many configurations each one of them would have. Yeah, so I think that's basically it. That is all I have for you guys. I will see you guys in class for our next flipped classroom activity. Have a good one, guys.